In this lecture, I will be illustrating the theory and fundamentals on heat transfer in furnaces that we have covered in lectures 28 to 32. I have found several examples in order to illustrate the theory which were presented in the said lectures. Now, in various situations, when we design a furnace, it is often important to know the heat losses which are occurring through a furnace. Heat losses, that means I am strictly meaning here the losses which are occurring through the walls of the furnace, that is through the lining of the furnace. Two situations are possible. In one case, there is already a furnace and you are required to know how much amount of losses that are occurring through the walls of the lining in order to modify, because you know that the loss of heat through the lining is in fact the so called loss of calorific value of the fuel. That is in fact loss of heat or the heat losses is equal to loss of fuel, and whatever amount of heat that you are going to reduce through the losses, you are going to save the fuel. In another situation, you are designing a new furnace and you want to find out what should be the optimum thickness for a particular fuel consumption. So, keeping in view both objectives in mind, let us see a particular problem to illustrate whatever I said in my introductory remark. All the theory and the necessary formula have been given in the lectures 28 to 32. Please see those lectures for the formula and the necessary details. Here I am writing a problem and let us solve that problem to illustrate the thing which I have said. So, a vertical furnace wall, is constructed of silica brick, with a total area of 400 square feet. I have purposely used FPS system just to illustrate the various dimensions and units, and a thickness of 15 inch. The furnace temperature is 3000 degree Fahrenheit, and that of surrounding is 80 degree Fahrenheit. Now, calculate A, heat loss through the wall. Calculate heat loss through this wall, of course, in British thermal unit per hour. Calculate fuel oil consumption. Fuel oil consumption equivalent to heat loss. Say in liters per day. For a fuel oil which furnishes furnishes 11,360 British thermal unit per liter of available heat. To the furnace. And C, you have to calculate thickness of silica brick, exposed to 2800 degree Fahrenheit. Now, here you take value of emissivity, of silica brick take equal to 0.8. Now, let us see how to solve this particular problem. Now, say if I take a solution A, say if I see the furnace, this is this one, this is the thickness, and thickness is given to us, a 15-inch is the thickness, and if this is the furnace, then the furnace temperature is 3000 degree Fahrenheit, whereas this is the surrounding, and this temperature is given to us 80 degree Fahrenheit. Now, naturally here, as I have said, that the heat transfer will occur from furnace to the wall by conduction, and from the wall to the radiation and convection. So, in fact, Q conduction, that is equal to Q convection plus Q radiation. So, given this heat transfer from the furnace to the wall of the silica, or to the wall which is exposed to the surrounding, will occur by conduction, and from the wall which is exposed to the surrounding, the loss will occur through convection and radiation. So, all that we have to say equalize both of them, and we can do that. So, Q conduction. So, let us assume that the temperature at wall of furnace exposed to surrounding, that is equal to Ts. So, that means that this temperature, let us say this temperature is Ts. So, in fact, Ts temperature is unknown. So, Q conduction, I am straight away writing down 3000 minus Ts into 400 into 1 upon 1.25, that will be equal to 0.2 into 400 Ts minus 80 raised to the power 1.25 plus 0.173 into 0.8, which is emissivity, into 400 Ts plus 460 upon 100 raised to the power 4 minus 5.4 raised to the power 4. So, what I have done, I simply utilized the left hand side is the heat transfer by conduction, the famous Fourier's law. The right hand side is the heat transfer by convection, which is H A into delta T, and I already given this particular expression for convection, and this is for radiation. So, all that we have to solve this equation, and this equation can be solved only by trial and error. So, we get by rearrangement at 3000 minus T s, that is equal to 0.2 T s minus A t raised to the power 1.25 plus 0.138 into T s plus 460 upon 100 raised to the power 4 minus 5.4 raised to the power 4. So, if we solve, so by trial and error we get T s, that is equal to 575 degree Fahrenheit. Mind you, all the formula which I have used to solve this particular problem, they are given in the lectures 28 to 32. So, now we can calculate heat loss. So, the heat loss, that is simply by conduction, that is 3000 and so on. So, this heat loss will be equal to 776 BTU per hour through a 400 square feet wall. Now, we can calculate the fuel oil consumption, and that will give you a feel which I said in my introductory remark, that heat loss directly correspond to the fuel oil consumption. So, fuel oil consumption, that is, this is your heat loss, and fuel oil furnishes 11,360 BTU per liter of the available heat, and this is in BTU per hour. So, if we solve, we get 68.30 liters per hour. So, if you assume that the furnace operates 24 hours a day, if the furnace operates 24 hours a day, then the fuel oil consumption that will be equal to 2049 liters per day. So, you can imagine this particular furnace, though is losing heat. So, this loss of heat, it correspond to loss of fuel, and you can see per day 2049 liters of oil is just consumed to maintain the heat losses which are occurring through the furnace. So, here you must be appreciating also that for efficient furnace design, it is necessary to optimize the lining thickness and thermal conductivity, so that the heat losses are minimum, because whatever amount of heat losses, that is the loss of fuel, and whatever you can save, you are contributing to the fuel saving and hence to the energy security as well as environment sustainability also, because whatever amount of fuel you will be saving, less pollutants will be discharged to the environment. Now, C part we have to calculate the thickness of the brick which is exposed to 2800 degrees Celsius. So, the C part straight away 776, that is equal to QC, that is equal to 3000 minus 2800 upon x, if x is the thickness which is exposed to 2800 degree Fahrenheit, into 1 into 400. So, this x, the thickness, that will come to be 1.24 inches. So, that means the wall of the furnace which is exposed to 2800 degree Fahrenheit is at 1.24 inch thickness. Now, let us extend this particular problem to another situation. Now, say addition of 3 inch layer of insulating material whose K equal to 0.12 to the furnace wall is being considered. Why? Because we want to see whether we can minimize the heat losses or not. Now, here calculate a percent reduction in heat loss, which would be attained by adding the insulation. B, daily fuel saving. If fuel oil cost rupees 50 per liter, you may substitute the actual price also here. And C, thickness of silica brick, exposed to 2800 degree Fahrenheit after adding insulation. That is what we have done. We have simply now modified this furnace by adding an extra insulating thickness whose thermal conductivity is 0.12. Mind you, in the earlier case, the thermal conductivity of the brick K was 1 BTU per pound degree Fahrenheit. This is K of silica brick in earlier problem. So, now if we try to calculate this one, same formula we have to apply. Now, what we have to do? What we have done here, say we have, this was our original, say 15-inch silica brick, and now we are adding an insulation brick whose thickness is 3-inch. Say this is 15-inch and this is 3-inch. So, here the temperature is 3000 degree Fahrenheit, here you have 80 degree Fahrenheit, and here again surface temperature one has to recalculate T dash S. Now, here this is a multi-layered lining problem. So, you have to again apply that multi-layered lining formula, again equate conduction is equal to convection plus radiation. I am omitting that step and I will like you to do that step, iterate it and get the surface temperature T s, which I am writing the surface temperature T dash S in case that will come out to be equal to 372 degree Fahrenheit. You have to do what? That is, you have to again Q conduction, that is equal to Q convection plus Q radiation. Only difference would be here you have thermal resistances offered by multi-layer, that is the only difference. So, then the heat losses, that will be equal to 315360 BTU per liter, BTU per hour. So, answer A, percent reduction in heat loss, that will be equal to 59.36%. So, you can see now adding a 3-inch insulating thickness of thermal conductivity 0.12, it has decreased the heat loss to the tune of 59.36%. Now, B, the fuel consumption has also decreased, is now 666.3 liters per day. So, fuel saving now as a result of this particular measure, that means addition of 3-inch insulating thickness, the fuel saving is now 2049 minus 666.3, that is equal to 1383 liters per day. So, that will correspond to, at the rate which I mentioned, around 69,137 rupees per day you are going to save by putting an extra insulation, and if you can convert on monthly basis or on annual basis by putting an extra insulating layer thickness on the existing furnaces, there will be a saving of money, not only money, but also you are going to save a huge amount of oil. So, that is what, to illustrate this particular problem, that the fuel saving and the economics, they are interrelated. Now, the last portion we have to calculate the thickness of the silica brick exposed to 2800 degree Fahrenheit is similar way. So, you have the losses 315,360, that will be equal to 400 into 200 upon x dash. I am omitting the steps, you can write down. So, the thickness of the layer which is exposed to the 2800 degree Fahrenheit is equal to 3.04 inch. So, this problem illustrates the so called use of the heat transfer in order to optimize the lining design, fuel saving and the associated phenomena like reduction in pollution, because you are saving the fuel and hence you are saving the pollutants also. Now, let us take another problem which concern to the design of furnace. Now, in several situations, so for doing experimental work, you require to design a furnace for doing certain experiments on the laboratory scale. The smaller furnaces you may not be getting in the market. So, you have to design the furnace. Now, let us take an example. So, we have to design a furnace, say design a furnace to carry out an exothermic solid gas solid reaction. An exothermic gas solid reaction on a continuous basis. On a continuous basis. Both gaseous and solid reactants, are fed continuously at 9.7 pound per hour at 70 degree Fahrenheit. The reaction products are to be discharged continuously, at 1200 degree Fahrenheit. Heat of reaction that is equal to 1050 BTU per pound of total reactant. The average specific heat the average specific heat of products of combustion are 0.2 BTU per pound degree Fahrenheit. Reaction chamber is a vertical inconel cylinder. It is a vertical inconel cylinder 1/3 feet in diameter and 3 feet high, and it has all facilities to feed and discharge the product continuously. The average temperature in the inconel cylinder, the average temperature in inconel cylinder is maintained at 1200 degree Fahrenheit. Now, the inconel cylinder is insulated will be insulated by a refractory material of which K is equal to 0.3 and emissivity equal to 0.8. Question: will a 1/6 feet layer of insulation making a total furnace diameter equal to 2/3 feet allow to operate furnace autogenously? Make suitable assumptions. So, this type of requirement is commonly at the undergraduate or postgraduate level of metallurgical engineering discipline. You are required to design a furnace so that the reactions are carried out autogenously. That means, you are not supposed to supply any heat from the outside. Whatever heat which is generated by the reaction, it has to be utilized for the reaction continuously. So, that is the problem under consideration, and you have to answer and you have to see whether 1/6 feet layer of insulation is sufficient or not. Means the reaction should be that means reaction should be carried out at 1200 degrees Fahrenheit, its temperature should not increase and should not decrease also. You are not supplying any heat from outside, remember. So, first of all, let us calculate heat input. We have to calculate heat input. Straight away it is 1050 into 9.7, that will be equal to 10,185 BTU per hour. Now, heat taken by POC, because it is continuous. So, heat taken by POC, that will be equal to 9.7 into 0.2, it is Cp, and temperature 1200, take environment temperature is 70 degree Fahrenheit. So, let us take environment temperature equal to 70 degree Fahrenheit. So, heat taken by POC, that will be equal to 2192 BTU per hour. So, that means the gross available heat, the concept already I introduced in my earlier lecture in furnace, that will be equal to 10,185 minus 2260, that will be equal to 7925 BTU per hour. Now, mind you, what does it mean? This means that 7925 BTU per hour of heat has to be transported from the furnace through the lining to the environment. If the heat transfer is less, then the temperature of the furnace will increase and you are not satisfying the requirement of the reaction to be carried out at 1200 degrees Celsius. If the heat transfer is more, the temperature will drop. So, the requirement is now what should be the thickness of the lining. So, in fact, if I see, so this is what the furnace is, it is a vertical inconel cylinder. This is the proposed thickness of the lining. This is the proposed thickness of the lining. This is it's given as 4 inch and here this is 2 inch and this is also 2 inch. This height is given as 36 inches. So, this temperature is a Ts and environment temperature is 78 degree Fahrenheit and this temperature is 1200 degree Fahrenheit. So, we have to see whether this 2-inch layer thickness is sufficient or not. So, we make certain assumptions here. Assumption number 1, that thermal resistance offered by the inconel cylinder is negligible. Thermal resistance offered by inconel cylinder is negligible. We have to justify because inconel cylinder has a very high thermal conductivity. So, it will not offer any thermal resistance to heat flow. And second assumption that we are doing, we will be taking average value of thermal conductivity, average value of thermal conductivity is used. However, you know that thermal conductivity is a function of temperature and as such one has to take for accurate calculation K as a function of temperature and accordingly to integrate it. But to illustrate the problem, we are making some simplified assumptions. Now, same as earlier problem, we have to do Q conduction, that is equal to Q convection plus Q radiation. Now, all that you have to substitute the formula and Q convection, as already I have told you for convective heat transfer in my lecture, that is say QC, that is equal to 0.28 Ts minus 20 raised to the power 1.25 into area. So, this formula is already known to you. So, if you substitute all these values, say conduction, it is in fact a cylindrical type of furnace. So, you have to substitute the value accordingly. I am leaving this problem, you should do it. I am simply write down the answer. So, if you calculate the Ts by putting left hand side and right hand side the formula and insert the numeral value which are given, the Ts will come approximately 400 degree Fahrenheit, and corresponding to 400 degree Fahrenheit, the heat loss would be 6523 BTU per hour. In fact, you should lose 7925 BTU per hour. So, what is the conclusion? The conclusion is that a layer of 1/6 feet is not sufficient. Is not sufficient on the argument that the heat losses are much less than heat remaining in the inside, what will it happen? It will raise the temperature of the inconel cylinder, and hence the reaction will not be carried out at the desired temperature. So, a layer of 1/6 feet is not sufficient to carry out the reaction at the temperature which is mentioned in the problem. So, the solution would be you have to think of other insulating material, of other thermal conductivity, or you have to increase the thickness of the lining, whatever the solution is available to you at that point of time. So, this is what in majority of the cases you are required to design a furnace and to see whether you meet your objectives or not, and this problem was in fact to illustrate those particular ideas. Now, in the next two problems I will be illustrating the heat transfer coefficient, heat losses by convection and radiation and their comparison. The problem is as under: in a 90 centimeter square flue, hot flue gas is flowing at 1.5 meter cube per second. Inside surface temperature of flue is 100 degrees C lower than hot gases. Calculate rate of heat flow from hot gas to wall per meter length of furnace when hot gas is dry air at 1200 degrees Celsius. Under three conditions you have to calculate: B, hot gas is moist air, and C, hot gas is flue gas. The whole idea of giving this problem is to let you feel that the radiation is through dry atomic gases. So, if we take the solution of problem under A, hot gas is dry air. So, here dry air contains oxygen and nitrogen, and heat transfer will purely occur by convection, because for the radiation to occur the triatomic gases like CO2 and H2O should be there. So, in A you have to calculate the heat transfer by convection, and first of all you have to calculate the heat transfer coefficient, and this correlation I had already given in my earlier lecture. There I am giving you the values, required values. So, if you substitute all these values into this expression, you will be getting, say, Hc you can calculate the heat transfer coefficient for convection, that is equal to 8.268 watt per meter square Kelvin. Remember, in A the heat transfer will occur only by convection, because there are no triatomic gases are present. That is what the idea of illustrating this particular problem. So, all that you have to calculate the heat loss by convection. So, heat loss by convection Qc, that will be equal to H C A into delta T, and all values are given. So, you are getting 2976 watt per meter length of the pipe, whatever the flue that is given to you. So, that is why you will calculate. Now, in another situation it is given that the gas is moist air. B tells that the gas is moist air at 1200 degrees Celsius with 2% moisture. Now, remember here the heat transfer will occur by convection as by radiation, because the air has 2% moisture. So, you have to also calculate the heat transfer by radiation here. So, in this B case the heat transfer will occur by both convection as well as radiation. So, for radiation I had illustrated in my earlier lecture 31. So, you have to find out first of all the length of the gas body with this formula 3.6 volume upon area. So, that will become 2.7 feet. Then you have to find out product of P into L, that is 0.022% moisture into 2.7, that will be 0.054 atmosphere feet. And as I said over there, you have to find out the emissivity, and from that the emissivity, that is epsilon g, that will be equal to 0.016. So, what I have to do now? I have to substitute now Q radiation as a formula which we have derived. I am not writing the formula, that is 1 into 5.67 into 3.6 is the area, upon 1 upon 0.016 plus 1 upon 0.8 minus 1, 14.73 raised to the power 4 minus 13.73 raised to the power 4. So, if you solve, you will be getting, this will come out to be 3819 watt. So, total heat transfer when the gas has 2% moisture, that will be equal to, so total heat loss, total heat transfer will be equal to radiation plus convection. So, radiation is 3819 and convection is that we have determined Q convection, that is 2976. So, plus 2976. So, the total heat transfer will be equal to 6155 watt per meter length of fluid. So, that is the whole idea, is to give you a feel that, well, in presence of moisture, there is a triatomic gas, the heat transfer will occur both by conduction and by convection and radiation, and this is very important when you consider the heat transfer in furnaces which contains CO2 and H2O. Now, the C part is a flue gas. Again, you have to calculate P into L. Now, here the same formula you will repeat. So, I have to determine epsilon CO2, that will be equal to 0.075, epsilon H2O, that is equal to 0.053. So, epsilon G, which is sum total of both, that is equal to 0.128, and I am repeating the formula Q, that is equal to 5.67 into area of the gas body upon 1 upon gas emissivity plus emissivity of the surface minus 1 Tg upon 100 raised to the power 4 minus Ts upon 100 raised to the power 4. So, if you substitute, then Q radiation, that will be equal to 29,722 watt per meter. Now, you see the heat transfer by radiation in presence of triatomic gases is a very, very important thing, and substantial amount of heat is transferred when the gases contains like triatomic gases. Now, another important thing is that to give you a feel about the radiation coefficient. Now, as you have seen, the thermal resistances offered by convection or by conduction, as well as thermal resistance can also be offered by radiation. We can consider the heat transfer by radiation in terms of the thermal resistance. So, we can straightaway write down, say Q, that is heat loss, that is equal to HR into A1 into T1 minus T2. Heat transfer by convection, we wrote Q is equal to HC into A into T1 minus T2. Here HR is the radiation heat transfer coefficient. So, now we can compare this equation, say Q we already know, that is 5.67 F A1 T1 upon 100 to the power 4 minus T2 upon 100 to the power 4. This equation we already know. Now, if we compare equation 1 and equation 2, then we can get HR value, that will be equal to 5.67 into 10 to the power minus 8 into F T1 plus T2 into T1 square plus T2 square is very simple. You just compare 1 and 2, eliminate, and you will get the value of HR. So, this is the heat transfer coefficient can be determined by using this formula. Now, if the temperature difference between T1 and T2 is very small, say T1 and T2 are nearly equal, then we can approximate this HR, that will be equal to 22.68 into 10 to the power minus 8 into F T to the power cube. Now, remember F is a view factor here. So, HR that will be equal to 0.2268 into 10 to the power minus 8 F T upon 100 to the power cube. So, with this formula one can determine the value of the heat transfer coefficient by radiation. So, when heat transfer involves both convection and radiation, then Q total that will be equal to Q convection plus Q radiation, or that will be equal to Hc plus Hr into delta T. So, if the heat flow path involves the circuit of conduction to the surface and convection and radiation from surface to the surrounding with the overall temperature difference delta T, then one can write down Q that will be equal to delta T upon delta S upon K average into A average. This is the thermal resistance offered by the conduction, and plus 1 upon Hc plus Hr. This is the combined resistance offered by convection and radiation into A. So, this is what another approach to determine a combined heat flow path from the furnace to the surrounding. Now, to illustrate this problem, this particular formula I mentioned, I will write a problem. The outside shell of a furnace has 327 degree temperature and surrounding is at 27 degree Celsius. Compare heat flow by radiation with that of convection per square meter of furnace. Outer surface area of furnace is completely surrounded by the environment, and emissivity of surface let us take equal to 0.8. Now, here again you have to invoke the, first of all you have to calculate the value of F, and F is equal to, you recall, 1 upon FBr plus 1 upon epsilon 1 minus 1 plus A1 upon A2 1 upon epsilon 2 minus 1, that is what the formula we derived earlier, and you also know that FBr that is equal to A2 upon A1 minus FB square upon 1 plus A2 upon A1 minus 2 FB. Now, here say since the furnace is completely seen by the surrounding, so FB is equal to 1 and A1 upon A2 is approximately equal to 0, because A2 surrounding area is very large. So, we can find out the value of FBr that will be equal to 1, and hence we can find out the value of F that will come out to be equal to epsilon 1, and if we take the emissivity equal to 0.8. So, we can substitute into the formula, say Q radiation upon A1 that is equal to 5.67 into 0.8, 6 to the power 4 minus 3 to the power 4. So, that will be coming equal to 511 watt per meter square. So, this is what. Now, here again just to illustrate, we can find out the heat transfer coefficient by radiation. So, HR that is equal to 0.2268 F T upon 100 to the power cube. So, if we substitute all these values, T is the average temperature. So, 0.2268 F is 0.8 and T is 600 plus 300 by 2 into 100 power cube. So, heat transfer coefficient by radiation is 16.53 watt per meter square Kelvin, whereas heat transfer by convection heat transfer by convection, we can say that is equal to 1.25 into delta T to the power 0.25. The formula already I determined. So, we determine, substitute the value, will get 5.2 watt per meter square Kelvin. So, by seeing the values of heat transfer coefficient by radiation and heat transfer coefficient by convection, it is very clear that heat transfer by radiation is much higher than heat transfer by convection, and this was the purpose of this lecture, was to illustrate the fundamentals of heat transfer by radiation in the furnace design, and that I have done through four problems.